predicting the weather. It's our pleasure to have Chris Daw from here and the University of Reading, and he'll be speaking about effective computations on weekly special laws.
Okay, thanks very much. And yes, it's my very last day today, so I will say thank you to everyone involved in the special year and everyone here, and yeah, I've had a fantastic time. Yeah, this is very much a work in progress, so I apologize for the consequences that might have, but we've been working on it for like quite a few years, so it felt like it would see the light of day. So the starting object is kind of one that's at the center of a lot of stuff this year. So I want to take a smooth, irreducible, complex quasi-projective variety. And the talk's going to be, it's going to have quite a lot of reference to degrees. So to sort of make that possible, I just embed this in Pn from the get-go. And then, yeah, true to the title of the special year, on here there's some Z variation, a polarized Z variation of Hodge structures. So then, yeah, I don't think Ben quite gets this in the lecture yesterday, but I think it's known to most of you, probably in some cases infinitely better than me. But sort of one way to sort of understand this construction is through the so-called period map. So S, of course, or the analytification of S has its universal cover. And then on, I take it on S tilde, there's a map by the period map that encodes the Hodge structure as it varies on S. So this is a space D, which is a homogeneous space for some reductive group G, real points of that, acting on some point 0. And we take this G to be what's called the Mumford-Tate group of the whole variation. So, actually, I'll just need one more piece of additional data. So this guy sits inside what Ben was calling D check, and I just want to record that that's a projective variety. Okay, anyway, the reason I put this on the board is because this gadget here endows S with a collection of sort of distinguished algebraic varieties called weakly special subvarieties. So you can get at them in the following way. Pick up any point on D, take this Mumford-Tate group, Q group that stabilizes all the Hodge classes, if you like, at the fiber of X. And then you take a normal subgroup, this group. This gives you then a subsymmetric space of D. So Dn is the orbit of X into N. These are sometimes called weak Mumford-Tate domains. And the weakness is the fact that N is just normal in N rather than the whole of N. Otherwise, just a Mumford-Tate domain. And then you look at an irreducible component pre-image under phi space, and then it's sort of a celebrated. So in the special case, I guess I'm not too sure of my history, but in the special case, when it's not weak, it's this result of Catani, Deligne, Kaplan that this is an algebraic variety. And then I think it actually came in the paper of Klingler-Otwinowska, is that right? That in fact, all the weakly specials are algebraic. This is an algebraic subvariety that I'm calling a weakly special. And again, yes, special if n was actually just all of n. And then I want to make one more slightly more esoteric notion. So I'll say that W is factor if I can make this construction, so I can choose an X such that the Mumford-Tate group splits as a product. So let's say n times n prime. So n was this normal group. Split as a product, and n prime should be something non-trivial. This then causes the symmetric space Dm to split as a product. And the dimension of Dm prime is tended to be 0 on this. And if I arise in this situation where there's some kind of positive factor around which some point can move, then I say I'm factor, and I'm non-factor otherwise. So I think this notion, this word, if you like, was invented by Umo in the Shimura case, and then it's used and extended by Klingler-Otwinowska-Urbanik. In general. And yeah, so it's these guys that I'm most interested in today. So, right, so just to recap, I have an algebraic variety, there's some gadget on it, and that gadget endows S with a special collection of varieties, which I call weakly special. Some of them are factor, some of them are non-factor, and I want to study these non-factor. So the motivation, what am I doing and where did it come from? So I'm, I guess, mostly interested in the Zilberpink conjecture, and the Zilberpink conjecture's most promising strategy is the Pilesanian strategy. And in that strategy, it's at least expedient to have some sort of notion of complexity of your special subs. So some natural number, if you like, and that you associate to your special subvarieties that allows you to count them. So such that the number of W special subvariety with complexity at most B is 50. And of course, there's kind of lots of candidate notions. There are discriminants and indices and blah, blah, blah. But the question is which ones to choose. So, several years ago, well, we were thinking about these things. We made some conjecture that, I don't know, maybe even was sort of known to people that know more. This was with Jimbo Ren and Ren and Javanpeykar-Kühne. And we essentially just said that for non-factor weakly specials, the degree is a reasonable complexity. So the number of weakly specials non-factor weakly special, which is the degree W times D is a finite collection. So I didn't know how to prove this at the time, but as I say, maybe people did. And Urbanik was the first person to write a proof, I believe. But far more than that, he gives a really explicit algorithm in the sense of how you actually might sort of tell a computer how to actually compute this.
So just to clarify for you, a CM point is non-factor.
Yeah. No, sorry. It's factor. Yeah.
So how does this go with this definition?
Yeah, so then I guess I'm allowed n prime to be everything or something like this.
Your Mumford-Tate group is just a torus.
Yes.
And so the adjoint is trivial, so n prime can never, like, it can't be factor under your definition. I think you need, because the thing is that your notion of non-factor does not agree with the notion of weakly non-factor in like our paper that you reference. And so like my result is for weakly non-factor, which is like it's the stronger condition.
Yeah, maybe I've been a bit cavalier because originally I wanted something like the centralizer in G add with M add, maybe in G of M add to be compacting the real, something like this. Yeah. So maybe I've been slightly cavalier with my definition, but no, I don't want to say that special is a factor because somehow this is a definition that's trying to separate the geometric problem from the arithmetic one, and
right.
Somehow I shouldn't be able to say things about CM points in this way.
Right. So like I think this definition works in like the Shimura context. Right. Like once you intersect with S or like take an arbitrary variation, it's something like more on an yes. Right.
I see. Yeah. I'd actually, yeah, let's continue that after. Yeah, that's very salient actually. Getting the right definition here is something we've been discussing. Anyway, so just to carry on. So one more remark, a little bit later, Klingler-Otwinowska and Urbanik with the following thing, which is that if you make the additional assumption that S is defined over Q bar, then, and again, using the right definition of non-factor weakly special, these are also defined over Q bar.
It's more like S and V are defined over Q bar.
Even just
yes, yes, that's a great point. No, it's a fantastic point. Yeah, just S gives me this, but you're quite right. There's something else one could assume, and I'm going to assume this from now on. So from now on, I assume S and the Hodge structure are both defined over Q bar. So okay, here there's some underlying algebraic vector bundle with connection, and if I'm getting the definition right, I just mean that algebraically that's defined over Q bar. And yeah, this gives me something additional about the Galois conjugations there. Non-factor weakly specials, but I'm not going to say anything more about that. So, cheeky enough for this mention. Right. So the question is then, I have finiteness and I have an algorithm. So how much more precise can I get about the complexity of these non-factor weakly specials? So let me make a crude definition. So I'm just going to say that the complexity of a Q-bar poly, sort of in any variables you want, is the maximum of its degree, the log height, the coefficients, and the degree of its field of definition. So this is maybe a bit crude to some people, but hopefully it's at least a precise notion. And then our main theorem is the following. There exists an effectively computable polynomial such that any non-factor weakly special of degree inverse d is defined by U-bar polynomials of complexity at most p.
Who's about the number of generators?
The generators. What the number of polynomials?
Yeah, the number of polynomials.
This must be part of it, but yeah, whether or not I can say anything intelligent at this point in time.
Yeah, it is, but I think it's even a formal consequence.
Yeah,
of
so
rather
it's
than-
formal of that, but somehow it's.
In fact, you can say that, I mean, it's valid for each of them, but also all of them, all the ones of degree D are defined. Let's see.
Just a remark. So of course you can ask about all the weekly specials. Of course, individually, there's certainly something about Cubanus, if you like, but we just prove the same, the analogous statement for the union of the weekly specials, you know, of some degree bounded by D. And then, you know, the non-factor weekly specials are somehow components. This sort of algebraic locus.
Can you usually tell, but there's finitely many pure polynomials of a given complexity, right?
Yeah.
That's the point. Okay,
Yeah.
Gaussian function. Okay, great.
I think so, as I made some London.
Yeah, by North.
But no, it's you.
I just forget what log height means. It seems reasonable.
No, I think it's a good question, because I think at some point I maybe made some exposition and forgot to put like the degree in. Okay, so let me try to come back down to earth, because this is all sort of mumbo jumbo. So let me give two examples. So my favorite one, as you know, is the modular curve squared. So what are the weakly special subvarieties? So to take David's point, if you get the definitions correct, I want to say you can have points and you can have lines, horizontal or vertical. And I want to say these are factor. Okay, so I don't really say anything on the nose about these. What is on the non-factor side? Well, primarily you're looking at the vanishing locus of the modular polynomials. Of course, you have y1 squared itself, but that's very interesting. So these are the non-factor ones. And yeah, I guess the vast majority of people see at some point this polynomial and see that it's an integer polynomial, which are variables. But then there's this famous result of Cohen that says that its log height, so the log height of phi n, is asymptotic to 6 psi n times log n, the same string. So that's obviously quite a precise thing. But in particular, what I want to say is that gives me about for any epsilon of the form degree. Let me make some shorthand for this. Let me call this Vn. Degree of Vn to the 1 plus. So, sorry?
What is psi?
Yeah, it's the Dedekind psi function. Oh, crikey. So if you take its, product decomposition, I think it's like p dividing n times p dividing n times 1 plus 1 over p or something.
Yeah, roughly. Yeah.
Yeah, that's the key. Yeah.
Your height is just the maximum of the height of the coefficient.
Yes. Yeah. Which I guess is just the absolute value, isn't it? Well, the log. So the point, okay, so I said two things in the theorem. First of all, I said effective, which, is something that we care about, and some people do, and some people don't. But I think the main point I want to stress is the fact that this is polynomial. So somehow the truth is like 1 plus epsilon. We can't do this, but somehow if you allow me to say polynomial at 1 plus epsilon is not too far away, then that's the main point. Let me try to explain one other one, which I don't know as well. So write U4 for the space of 4 variable polynomials. Homogeneous of degree 4. That define for you a smooth surface in P3. And then there's this famous sublocus of this collection of polynomials called the Lairez-Sertoz locus. So that's just the F's where the rank of the Picard group of the surface. So I should give this a name. Next step. The rank of the Picard group of the surface is at least 2, so it jumps. Which is tantamount to, so if you prefer this way, it's sort of tantamount to saying that there's some Z linear dependence between its periods. And you can break this locus up into algebraic pieces, and you can do it in a few different ways. So the way I do it here is to say, take the fundamental class, the generic hyperplane, fundamental class of generic hyperplane. And then you get this delta on H2, which sends gamma to the intersection product of H with gamma squared minus 4 times gamma gamma. And you can define then NL, so for some delta positive, you could define NL delta to be the F NL, where there's a gamma in the Picard group. Such that delta of gamma is delta. And so this was one of the key inspirations for us. There's a recent result of Lairez and Sertoz that says that the log height of NL delta is bounded by an exponential in its degree. So C to the degree of NL delta. But they have some heuristics, and they conjecture that in fact this log height, I should actually say, sorry, just before someone asks, this actually really is given by a single polynomial. It's a large number of variables, so the log height, and it's actually integral. So this really is again some log of some absolute values, and they conjecture that this is in fact of the same flavor as Cohen. So it should be for any epsilon degree to the 1 plus epsilon. Where else did it jump off? So, yeah, so they've conjectured 1 plus epsilon again, which I guess there's, limited hope of achieving, but somehow we bring an exponential bound down to polynomial 1. And so lastly, let me just say one more thing about this work. And this was their motivation. They used this height bound to then produce some kind of separation bound for periods of quartic surfaces. So they phrase this a bit differently to us. You can take something in H2 and pair it with the holomorphic 2 form, and either this is 0, or you can say how non-zero is it, right? So they phrase it like this. Yeah.
I have a question. So your work and that work is about upper bound the height.
Yeah.
What's about lower bounds?
Oh, good question. For the height. It's a very good question. I didn't prepare.
I think there's a pretty precise bound for the degree by maybe it's 9/2 or something like that.
A lower bound?
I think it's a precise asymptotic for by Pande and then. So I mean, and then it's really a matter of how you define the height precisely. Like whether you normalize by the degree or not. I mean, to give a precise height lower bound depends on how you define the height for a hypersurface, and this might be normalized by the degree. I mean, it's.
Oh, I see. And you're saying that how you define that level of precision doesn't.
Yeah, I mean, you have a statement here which.
Which has an upper bound.
Yeah, but I'm saying, so if you took, for instance, the sum of the coefficients or the maximum of the coefficients, but if the degree is this delta to the sum, delta to the number 2, and you take the sum, then probably the height is at least also equal to the degree. I mean, if you take the maximum, maybe you can expect something smaller. Then
But that theorem is not sensitive to how you define it.
Yeah, because in that theorem, it's always a polynomial and a degree.
Yeah.
Okay. I see. But how about that conjecture though? It seems like that conjecture should be sensitive on how you define your.
Yeah, I mean they do. Yeah, okay. Their height is what they call the one height, so it's the sum of the absolute values rather than
Of the coefficient.
Yeah.
But because you took a sum, it's at least going to be the degree. You see, or okay, unless they're all 0, but I think it's going to at least be.
No, it's a really good question. I apologize, but we can look into it. Yeah.
Can I also ask, I guess, on the topic, so if you vary the degree of the K3 and just take the discriminant of the lattice there, so now H squared is in there, is this like, expected to be like, you have some uniform estimate now?
Oh.
So, like this is for like quartic K3, so now I want to vary the degree of K3, so it's a bunch of different moduli spaces, but sort of in delta, now include H squared.
But I suppose there's no way to sort of package those in one moduli space, right?
No, yeah.
Actually, no, I think
you
there
have
might
things.
Yeah.
No, actually there will be. You can put all of these things inside an orthogonal of every dimension 1 high. Your theorem is not just for divisors, right? It's for all special subvarieties.
Exactly.
Okay, then I think you should be able to get independence because all your model of K3 is like a bunch of orthogonal varieties of dimension 19 or something. You can put them all inside
Oh,
a
beautiful.
fixed variety of dimension
Oh,
between
right.
20 and 22. I think would that.
Fantastic.
19? 19 inside. We want, okay.
Okay, yeah, nice.
Nice.
Right, so So we can do some separation of periods. This is theorem 2. Again, there's an effectively computable polynomial P such that and now I give you two things. So I take in S a non-factor weakly special of degree at most D. And a Q-bar Hodge generic point in S. Sorry, so Hodge generic means not contained in any special subvariety. Then I can choose a lift from this S such that the log distance in D check, so some really steady distance, if you like, between the image of S tilde and Dn, which I didn't define. So here's a non-factor weakly special, and so it naturally corresponds to some choice, some weak Mumford Tate domain Dn. And I want to say that the log distance between the period image of this S tilde and this weak Mumford Tate domain is bounded from below by the reciprocal of this polynomial evaluated at D, the log height of S, and the degree field of definition. So somehow these things all have to be here. We get some polynomials, I guess, reciprocal polynomial strengths. The distance.
So quick clarification.
Yeah.
Will your theorem work if S is just not an S of Q bar? Or like
I don't think so. Yeah, I really because this is going to be some sort of Liouville application.
Okay.
And
Uni generic.
oh, sure. Yeah, this
It's
generic.
how generic that I.
That's a very excellent question. I've only put Hodge generic there because that's as far as we've got.
But you expect
There's scope. Yeah.
Also, because maybe outside the Shimura case, maybe there are no hot genetic points defined over Q bars.
Right. I did, as I was writing it down. Yeah. So as I say, yeah, this is definitely this is for safety, right? At the moment.
Okay, this is easy to formulate. We can say something also for non-generic, but yeah, we didn't. We're some more technical.
I go home tomorrow. So. Okay. Do I have time? So just very quickly. Yeah, I don't know. Maybe this will kill the time at the end, but just very quickly again, just to sort of ground things. So just very classically, if you take Cohen, and then you take these Liouville or Warasevich bounds, this would tell you so now I'm just working on y1 squared, but I could take the log distance there, and I could sort of say, well, how far can a Hodge generic point be from the vanishing locus for modular polynomial? And I didn't do this so carefully, so I just put a little tilde here, but it should be something like degree of the field of definition, the degree of Vn. I seem to think I needed 2 plus epsilon here, times the sum of hx plus hy, all to the minus 1. So if I give you the height, then I can do these usual things and get some separation. Okay, so some words about on the proof.
Here you find it distance in
Yes.
S, not on the periods.
Yes, that's right. Sorry, I just did one step. Yeah.
But like the harder part of this theorem is to go to the periods.
Yeah, sorry, I should have said that. Yeah, so this is step in the proof, because I might not get there. This is step one, but then I somehow have to transport this to a bound in the period domain, which requires some additional machinery. Okay, so the proof. So there's some standard gadgetry around. So I let gamma be fundamental group, some base point. And this, of course, has a monodromy representation. So to G of Z, G of V, where V is 5 or S0. And usually you can take the image of the sky, take the Q-Zariski closure. That's called the algebraic monodromy group, and this is a normal subgroup of G. And again, for some safety, because there's some subtleties that I understand, I actually want to just replace G with the normalizer of this H in GL. That's just then comes the main gadget. So there's this bundle P that I construct analytically. I take S tilde and I take complex points of G and I just mod out by the diagonal action gamma. I call this the standard principal bundle because I follow Mill standard principal bundle. Some people I think call it the period torso or maybe some other things. And this is an algebraic G bundle endowed with a canonical variation. And there's two important maps on this guy. So there's the projection down to S. There's this map into the period domain, which I call beta. And so we had a paper before where we were studying geometric Zilber-Pink or some effective version. So we did lots of these things before. And this is kind of a bit of a baby version of this. I think probably to some extent also included in the more recent paper of Boldi and Urbanik. But I want to say that there's some locally closed locus, which I call pi KD, size P. It might only be constructible in P, but I sweep this under the rug. That parameterizes the weakly specials subvarieties of dimension equal to K and degree of ST. And moreover, this locus has the property that if I take an irreducible component and I send it down to S, and I take its Zariski closure, then these things are precisely the non-factor weakly specials. Okay, so there's some relatively straightforward way to define algebraically the locus that we're interested in using this gadgetry here, which I sometimes think of as some kind of algebraic alternative, this kind of analytic one that we started with before.
So the locus that you're talking about is like the union of all the subcourses corresponding to the weekly special.
Yes, I don't actually think we have to sort of go through it. It's quite as complicated as that, but in the geometric subgrouping, that's exactly what we do. Yeah. There is a tiny bit of functional transcendence here, namely precisely that the weekly specials are exactly the bialgebraic subvarieties. So there's kind of the very first step of functional transcendence. Okay, then we need some tools. So now, okay. Now clear the board. I want to just kind of start again. So this is, let me call this differential algebraic geometry. And you might have to refer back to this setting, so I'll just call this DAC. I'll use some suggested notation. So suppose you have P, smooth, quasi-projective variety. Suppose it has a foliation. And I'll write LP for the leaf through P. Suppose X in P is a subvariety. Suppose we have a map. It goes from P to S. And right, so and then everything I want in some kind of projective space. So this one will be in some P and P, and this one will be in some P and S. And assume that all of this data, I guess it's apart from this thing, is defined over a number field K. So just some axiomatic framework. And then in this setup, make it a definition again. So I'm reusing notation kind of suggestively. So I say pi KD is the locus of points in P for which there's a subvariety W in S having dimension K and degree at most D, which contains an irreducible component of the image of LP intersect X down in S. Then, so I'll call this an approximate theorem because it's quite on the nose. One can compute effectively a polynomial P such that this locus pi is again defined by effectively computable Q-bar polys of complexity most P of D. And this is the main tool. This is really where everything else is kind of depending on this. And I wouldn't usually get, heavy into the proof here, but like, I just want to say a few words just to try to explain why, in some sense, where you went from exponential to polynomial, I suppose. So the proof is essentially like this. You make some reductions. So in particular, P is affine. X is smooth. You do several other things to make the situation nice. And in particular, it suffices to look at the case where W is a hypersurface. And then the trick is as follows. So let PD be just the space of degree most D polynomials in NS many variables. And then there exists a linear map. Linear is the key here, which I call LD, which goes from this space of polynomials to global regular functions on P or R tuples of those. And the key property of this linear map is that I'm in this locus. Now remember it's hypersurfaces, so pi dim s minus 1 d, if and only if the kernel of this map, when I evaluate at P, is non-trivial. So somehow this fancy locus here, and they want to compute, I can somehow compute by the vanishing of the kernel of a linear map. And so in particular, this guy is just defined by the dim PD square minus of LB.
Chris, can you write it in that kernel a little bit bigger?
Sorry, sorry, I was getting a little bit cramped there. So, yeah, what I want to say is, I have a linear map that goes from a space of polynomials to regular functions on the whole of P. And I want to say that, when I post-compose with, take the value of my P, I write that E.
Oh, I see.
So now I just have a linear map from this vector space to the C to the R. Then if it's a linear map with non-trivial kernel, then precisely saying that I'm in this locus. So somehow this gives me much time to control on the polynomials defining it. Sorry, I know it's almost impossible to.
There is the subscript on LD inside your brackets.
Is there a question? Yep. Thanks. But that's the point. That's the only point I want to stress. That somehow, there's some linear determinant-like condition that allows us to define the locus. Gauss genius observation, and this is.
So can I ask just sort of roughly what's happening here is a polynomial, you want to detect if you get some weakly special thingy, you have this foliation space, which haven't thought through yet. But is the idea you sort of write out the germ and you write out the explicit sort of formal condition that we're expecting something linear behind the order, that's your polynomial?
Yes. Okay. So maybe Gal, do you want to answer the question?
Yeah, you're trying to figure out whether a polynomial vanishes on a leaf or when it's a leaf intersected with something and project it. So basically, you can take a polynomial and look at its jet, expand the jet, and you want the jet to be identically zero.
Yes.
Then that's equivalent by multiplicity estimate to just checking a jet up to some order.
Okay, I was gonna say that, the multiplicity estimates are not the deep part of this, that's sort of.
So I mean,
stuff for-
that is multiplicity estimate, and it just tells you that, if you're looking for whether there's a polynomial and the dimension is identical, it's enough to check the jet up to a certain order. But I mean, the crucial thing is that this is linear in the polynomial, right? So you can just write a determinant. And the entries of this OP of R are all of degrees that are also polynomial in the original degree. So eventually these minors that you get, they're actually a polynomial degree in the initial data.
Yeah, exactly. Right, so to finish the proof, I just apply this to theorem 1. I mean, that's a bit vague, but somehow we can maybe believe that this pi kd in the first setting is somehow related to pi kd in the second. Gives me the equations that I claim to have. So lastly, separation bounds. And yeah, so there was a very good point about my sloppiness. So actually, sorry, let me make one more remark. So you can also use this tool to get the following theorem. But also you can get some effective polynomials P such that if W is a non-factor weakly special of degree D or degree of most D, then this guy has some algebraic monodromy group HW, and then if I define GW slightly unorthodox to be the normalizer in G with HW, then I can say that the period torser or the standard principal bundle associated to that G, which is a subbundle, the GL bundle, this is defined over QR, but with equations, Q-bar polys, Q-bar equations that say of complexity. Again, at most, E of D. This is kind of an additional observation we had. Yeah, about these period courses. Yeah, rubbing that off was that's the idea. Okay, anyway, so to the separation bounds. As I say, if you take the height bounds from theorem 1 and you add sort of Lovo-Wojciechowicz bounds, this just gives you straight away the log distance between S and W from the theorem is bounded from below by P of the invariance to the -1. There's nothing new contained in that statement. And so, as Gal says, somehow the difficulty is then passing that distance bound over to the periods, the period domain. And so to try and, I don't know if this is a good picture, but what you might imagine is that like you have S and it gets mapped to the period domain. Maybe I'll use S tilde. And you get a weakly special. So there's some intersection with some weak monthly. So somehow this point here is maybe like the shadow of the intersection of W, if you like. Maybe I'm looking through a cross section or something. But the way I've drawn this diagram is supposed to make it look like they're quite tangent when you go into the period domain. And so if this is S or S tilde, suggestively these might be quite far away. Whereas if you have a high degree of tangency, this distance here might be quite close. So this is the thing that you're sort of fighting against. So we have to use another of Gallus' tools to get around this. Here's an approximate theorem again. So go back to the DAG set. So we just have this P, the affiliation, and the subvariety. And then you have to watch out for this locus sigma, which is the collection of points P on D, where the dimension of X intersected with the leaf through P is larger than you'd expect. This is somehow the thing that works against you in some vague sense like this. But then, if you have a point, P say, and the distance between P and X is small, so say smaller than some epsilon, this implies that there actually exists a Q that sits on the leaf intersected with X, such that the distance between P and Q is smaller than 1 over the dimension of X over the distance to this bad locus. And so somehow this is exactly what you need, because we can now use the same DAG machinery to compute this locus. Yeah. And so in particular, we can do LL again, and we get some control on this distance. And then somehow this pathology up here can't happen because we somehow say that this sigma is also controlled by the weakly atypical locus. And so I was Hodge generic, and so somehow far away from this. And so if the upshot is, if I'm far away here, I have to be far away in the period space. Like these two things give me some compatibility between those distances. Anyway, so I think I'll stop there.
Great, thanks. Any questions?
You just like repeat that last argument. I feel like I'm
It's hard to say it because I didn't want to get into the.
No, and just like the log distance above that you have bigger than P inverse.
Yeah.
That's the caliber of bound you want, right? That's not
Exactly.
like up and
I want the same bound in both places. Yeah, exactly.
Okay, great. Yeah. Mhm.
Yeah. So yeah, let me see. So I suppose it's an argument by contradiction or positive or something. So the thing is, suppose I was close in the period domain. Right, so suppose maybe I could put it here. So suppose something like this happens. So remember there's take here. Well, this, yeah, so what, it's very hard for me to explain this without using the gibberish that I have up here. So what this says is that I can work in P, convert this being small, this being small. So you see, what this is like, the way to think about this beta minus 1 of dn is somehow like all the translates of dn. So I get that this is small, and then I apply the theorem. So this is like this one being small.
And so then what this says is that I get a point Q that's also on the leaf, but on this X, where X is now this guy here. So I'm going to get a Q that sits on the leaf, also on this right. Yeah. I suppose maybe these should be shown. This is too complicated, but this is homeomorphic to, or diffeomorphic to just this, where, how do I get this G? The P I took here is precisely the class of S tilde comma G. Okay, so this,
I guess my question is, I'm trying to understand, like, in principle, you can have, imagine a map from a curve to a, whatever, a period image or something, or a variety or something.
Yeah.
And you can imagine 2 points on this curve.
Yeah.
Get very close, the period image, but
Yeah.
they're very far on the curve.
Yeah.
Are you somehow ruling that out? or
Yes.
You are ruling
Well,
that out.
what we're saying is that because, yeah, there's some bad locus where you can't rule that out, right? That's this thing because yeah, this yeah. So, and first of all, we can compute, equations and heights for this and therefore control this. But then the next question is, well, what is this locus? And then we basically say that this is essentially the Hodge locus. So if I'm Hodge generic, I'm not on here, and so my distance from here is controllable. That's that thing there. And then my original bound gives me. Sorry, these are less than.
Maybe that's what I'm missing. Why is it controllable? Like in the case I'm saying, the Hodge locus would be like pairs of points that agree.
Yeah.
And so let's say I don't have pairs of points that agree, but I have pairs of points that are very, very close. How do you tell me that they're in fact not that close, or give a bound for how close they get?
The point is of bounded height, right? So you have an algebraic point of bounded height, right? So
On the curve,
on the curve.
yeah.
So it either sits on the sigma or it's.
But how do you know that I agree it's not close when there's some actual number, some delta is bigger than it. But how do you compute this delta?
Yeah, sorry, I think the reason I've confused you is because when I write this bound here, P, I just put this line here. And of course, what goes in here is D, the degree of the weakly special, the log height of S.
Yeah.
It's for the definition. So when we say close, small or whatever, we're saying, in the terms that you would expect from, what the Neuville Woisevich bounds give you.
I see. This part's only for Shimura varieties or for?
No,
In general, I'm just confused. It seems like you're saying if you have two hard structures that aren't the same, and you know the height of the point, sort of, which gave you those hard structures, you can tell me something about, they're at least epsilon apart from each other. And that's.
I mean, there's a rigidity assumption. So I mean, if you just took different ones, it wouldn't be. I mean, he's only looking at like one of these like rigid things. It's non-factor weakly specials. So it kind of wouldn't come up in it. So if you took the locus of points that are equal, so that's the same as a diagonal. You can do it in the you can define this algebraically on the curve as well.
Okay, so somehow the thing I'm talking about doesn't come up. Where you're just.
The thing you're talking about would be like the non-rigid case. You just took 2 points.
Yeah.
That's our Hodge, CM point. You could take 2 points like that, but okay, that wouldn't be non-factorial.
Okay, maybe I'll ask later.
sure, yeah, sorry, thank you.
No, thanks for that.
Other questions? I have a question, but it's too stupid, so I'm gonna ask you after. So, if there aren't any other questions, thank Chris again.